So now let's look at some exponential applications. So what exponential graphs look like is there's kind of two forms to them. So I'll graph them up here for you. There's exponential growth, which would look like this. So for reading left to right, it's an increasing graph. Now it almost looks linear, but it has curvature to it. So there's a curve as it goes off to positive infinity. But it's kind of the same idea of like if we looked at a point, there'd be this kind of positive slope. It's a little more difficult to visualize rather than a straight line, but there's this increasing nature to it. And then our other form is exponential decay. In fact, let me write that down. This is exponential growth. So the output values are getting larger. And this next case is called exponential decay. Which looks like this. So with exponential decay, we start with large values, and then the outputs get smaller and smaller and smaller, and then eventually they approach zero. So there's this idea of approaching zero in the long run for both of these graphs. It's kind of like with exponential growth, we're starting from zero and then growing from up there. Now, with these, like comparing exponential graphs with linear graphs. Linear graphs have slope to them, and that slope stays the same as you look across the entire graph. So there's this constant rate of change. With these graphs, the rate of change changes as we read left to right. Where we have certain growth over one unit, it changes over the next unit. And it's typically by a multiplier. This is coming through multiplication of values. Whereas with linear is like adding on values, like you move one to the right, so you add on 2. That would be our slope of positive 2. You move one to the right, add on 2. Move to the right, add on 2. With these, it's multiplication, so it would be something like, if we move to the right, double it. Move to the right, double that. So you're multiplying by a value as you move along. So how that shows up in our equation is, the key word is that it's exponent, it's exponential. So if we look for our variable is stuck up in the exponent of our equation. So if you've never seen these graphs, again, this is more about interpretation. So I just wanted to show how you can recognize whether or not it's exponential. It'll come through as that growth or decay. And then if you look at the equation itself, you'll see the variable and the exponent. And then from there, we're really going to rely on Desmos to help us out with solving, since we won't expect you to solve these algebraically. In fact, for some of these, you would need logarithms, which we absolutely do not cover in this class. So don't worry about solving these algebraically. It'll be more about grabbing values from Desmos. So with this one, you're starting a new job, and you have this initial salary of $36,000. And often with these exponential equations, there's this idea of a starting value, or we call it initial value, just to give us some terminology. So is that we'll have this starting value, and then from there, our graph is growing or decaying. Since we're dealing with salary here, we're hoping for exponential growth. We're hoping our salary isn't decaying here. So each year thereafter, you receive a 3% raise. So there's our idea of exponential growth. So when we look at our graph, we should be seeing something like this. So we'll see the salary growing as time is passing. So we're going to let S be your salary, T years after you start your new job. So we're having this growth of 3%. It's like with that, it's this multiplication. It isn't necessarily multiplication of 3%. It's kind of like multiplying by 103%. So if you've looked at the financial math section already, this idea is kind of in there of this growing value based on a percentage. But our salary would grow by 103%. Because, for example, like if my salary was $20,000, if I take 3% of that real quick, let's see, 3% of 20,000. That would be 600. So 600 is not my new salary. That's how much is being added on. So it's like I want that 20,000 plus that 3%. So I have 100% of my original value and 3% of that salary. So in total, we're taking 103%, and that is where that 1.03 is coming through. It's the decimal form of that 103%. So we have our starting value and that. I will not ask you to make these functions. I just want to show you where those numbers are coming from. Okay, in terms of the work you'll actually be doing with these. So what will your salary be after 10 years? Now this isn't too bad to solve for algebraically, but I'll show you the calculator first, and then we can we'll use the graph, and then I'll show you on the calculator how we could do this. So we're setting t equal to 10 here. So let's go ahead and graph this 36,000 and 1.03 to a t. So 36,000 is my starting value, and then times 1.03 to x. Oops, that's x. Now, I can't see that at all, but if you think in terms of the graph, it's like when time is 0, I'm going to be graphing 36,000. So even if I start zooming here, it's going to take me a long time. So this is where adjusting my graph will be really helpful. So what I can do is for my y-axis, let's go ahead and I'm going to keep 0 in the frame here, but I'm going to go up to, let's just play around. I'm going to go to 50,000 because I definitely want to see above 36,000. Oh, that's not too bad. That's great. And it's a little off screen down here, but I can see my value for 10 there and get an idea of where that's landing. Again, that scrolling is kind of hard, so it's hard to get an input of exactly 10. So what we can do is similar to what I showed in the last video. However, this time I have my value for x. So we know x equals 10. So if I plug that in, it'll graph the vertical line at x equals 10, and I just need to see what that intersection is. So when time is 10, we have 48,380.99. 48,380. And done. That's it. I'm just grabbing from the graph. We just need to adjust our axes so we can see everything clearly. With this one, if you wanted to solve algebraically, it's not too bad because you're just plugging in that value of 10 for our exponent. And with that, you can just go to a scientific calculator. And let's see, exponent of 10. And there's that same answer. So with that, you can use the graphing calculator or scientific calculator to solve that one. In fact, let me put a note of that on the side. Graphing or scientific. This next one, however, scientific. Okay. When will your salary reach 72,000? So with this one, we know what S is. So if I plug that in, I have 72,000 equals 36,000 times 1.03 to the t. I'm going to get to this spot where I need to solve for an exponent, and that's what logarithms do, and we are not covering logarithms. So with this one, I definitely want to use the calculator, and especially the graphing calculator. So we have to use graphing for this one. So what I'm going to do is I already have this part of the equation plugged in. That's what I'm graphing. And I just want to see where is there an output of 72,000. So this is where I'll graph a horizontal line. And actually I need to extend my y-axis because I need to see to at least 72,000. So let's go up to 80,000 just to bump it up a bit. And I'm going to change this not to x equals, but y equals, because I want a horizontal line. And 72,000. There we are. And there's our intersection. So 23.45. So from that, you get T equals 23.45. So when will your salary be $72,000? After 23.45 years. So that's how we can use the graph. Given an input value, you can either use the scientific or graphing calculator to solve. If they give you an output value, we'll have to use the graphing calculator. Unless you know logarithms and want to go for it, but that's not part of my expectations for this course. Alright, let's do another example here. So after caffeine is consumed, it leaves the body at a fairly fixed rate. So we're going to see this exponential decay. After we consume caffeine, we'll kind of have this initial value of caffeine, and then it wears off over time. And how it wears off is exponential. So a person consumes 200 milligrams of caffeine at 8 a.m. and then 4 hours later, about 100 milligrams of caffeine are remaining. And that just made me realize I'm going to change part B a little bit because they just gave us one of those answers. I'm going to change that to 150. Okay, sorry. 4 hours later, about 100 milligrams of caffeine are remaining in their bloodstream. Let Q be the number of milligrams of caffeine in the body, T hours after consumption. So we're going to have the formula here. And again, I can tell this is exponential because our variable is an exponent. Now, if you take a look at 200 is that initial value. We're starting with 200 milligrams, kind of like how we saw in that last example, how we started with $36,000. And then we were growing by 3%, so we have this value over 100%. What you can notice here is that the value is below 1, so it's below 100%, and that's where decay is coming through, is that it's shrinking. So you can kind of tell whether you have exponential growth or decay by that number right there, and whether it's over 100% or under 100%. Okay, write two ordered pairs for this scenario in the form of hours after 8 a.m. and milligrams of coffee. So let's look at our two pieces of information. 200 milligrams of caffeine at 8 a.m. So that would be the idea of 0 hours after 8 a.m. and 200 milligrams of coffee. Our other case is 4 hours later, so 4 hours after 8 a.m. and 100 milligrams of coffee. So we have these two coordinates that we'll be able to see in our graph. All right, how much caffeine is left in the body after 2 hours? So with this, we are looking at T equals 2. Let's go ahead and assume when it says after 2 hours, it's like 2 hours after 8 a.m. So after we consume our cup of coffee or whatever we're drinking. After 8 a.m. So we have this value. Again, whichever way you want to go, you can solve for this algebraically or using the graph. This would be the idea of just plugging in 2 for the amount of time. So let's get the graph going here. I'm going to have a very different scale for this one, times 0.8409, and then exponent with our variable. And I can see my graph is down there. I am going to zoom way in. I'm going to kind of have this largest value for y of 200, because it's like we're starting at 200 and then decaying from there. So maybe I'm going for 250 maximum. Oh, and then my y-axis is way down there. There we go. That's pretty nice. And then I can just, you can also just pick up the graph and move it too if you don't want to fiddle with the numbers, but sometimes it just helps to get those numbers set. So it's like I'm plugging in 2 here, so if you want to, you can just type in x equals 2 and look at the intersection point. So 141.423, or if you plug into the scientific calculator, you get the same thing. So Q equals 141.423. I'm just going to double check that number real quick. 423. Great. And so that means that's the number of milligrams. So 141.423 milligrams of caffeine. how much caffeine will still be in the body at 8 p.m.? So this is 12 hours later. So same routine, if you want to plug in algebraically, you can plug in 12, or we can use our calculator, the graph. We could just make that 12 and look at that intersection point, so 25.001, so about 25 milligrams. And when will there be exactly 150 milligrams still in the body? Again, I changed that because that question before of when will there be 100 milligrams is answered right there. So I need to change that a little bit. So this would be that Q is equal to 150, and we need to find what time is. And this one we have to use the graphing calculator to help us out, since we're not doing logarithms in this class. So I want to look at y equals 150. And with that, I can get that intersection point, and t is 1.66. So let's see, this is 1.66 hours after 8 a.m. That is a correct way to answer it. We could also get specific with the amount of time. Let's see, this is 1 hour and it wouldn't be 0.66 minutes. In fact, that makes, it wouldn't be 66 minutes because that wouldn't make any sense. Rather, it's like 66% of an hour. So what I'm going to do in a calculator, in fact, let me just show this. I would take, 60 minutes times 0.66. So that's about 39.6 minutes. I'm going to go ahead and round that to 40 minutes. So this is like 1 hour and 40 minutes after 8 a.m. So we could also say this at 9:40 a.m. So there's some different ways you could answer it. If you're writing on a written assignment, you can do any of those in my open math in my desk for a specific form to answer in. But yeah, so those are exponential applications, seeing exponential growth, decay, and just really relying on that graphing calculator to help us solve.